In these examples, we want to take a look at the trapezoid rule and see how it works and how it can be used to approximate an integral. Because sometimes we'll have functions that it's rather hard, if not even impossible, to find the antiderivative. The idea behind the trapezoid rule, as we can see here, is that instead of using rectangles to approximate the area, I'm going to use trapezoids, and you can see, kind of compare, if you visualize some rectangles in there, that trapezoids are much closer because they have that slant. Instead of assuming that it doesn't change on the interval, trapezoid rule assumes that there's a constant change, kind of like a straight line. And so we divide the interval up into our partition, just like we did for when we set up our Riemann sums, when we set up our right-hand endpoint rules. And you have x0, x1, x2, xn minus, all the way up to xn minus 1 finally, xn, which is equal to b. So if you move down here now, when we look at our trapezoid, here I'm just looking at one interval from xi minus 1 to xi. Now you might recall that the area of a trapezoid is 1/2 the base, sum of the bases plus the height. Here I am looking at my two bases being these two sides. My trapezoid and the height being this third side here. Okay. So now the height at this point would just be the point on the graph. So that's actually just going to be f of xi minus 1. And then this other one's going to have a height of f of xi. So we know those two. The height, which is this side right here, is going to be the difference between xi and x minus 1, which is just delta x. And so we have area equals 1/2 f of xi minus 1 plus f of xi all that times the height, which is just delta x. And we do this for every single interval, and then we want to add them all up. So that's just the area for one interval, one subinterval. We do it for all of them. So a couple things I'm going to do here is I'm going to factor out the 1/2 delta x. So we approximate our area. Area is approximately 1/2 delta x. And then for the first one we'd have f of x0 plus f of x1. We're using my area formula. And so that times delta x times 1/2 would be the area for that rectangle. And plus, the next one would be f of x1 to f of x2 and then f of x2 to f of x3 and so on until we get to the very end where we have f of xn minus 1 plus f of xn. And what I want you to notice here, and the key to coming up with the formula for the trapezoid rule, is noticing this fact now. And that is, except for the starting point, the f of x0, f of x1 shows up twice. And so does f of x2. So those parentheses then inside there can all just be dropped, and you can combine like terms. And so will f of x3. F of x3 shows up its own time. And then it'll show up again in the next term. And so on, all the way down the line. The term before this would have been f of xn minus 2 plus f of xn minus 1. So that guy gets duplicated. The two guys there, f of xn and f of x0 being our endpoints, don't get duplicated. And then the second thing, what is 1/2 delta x? 1/2 delta x, well, that's just 1/2 times b minus a over n. That's just b minus a over 2n. And so the trapezoid rule tells us that the area can be approximated by doing the following. Taking b minus a over 2n times f of x0 plus 2f of x1 plus 2f of x2, and so on and so on and so on. So we'll have 2f of xn minus 1, and then the last guy, the guy on the end, f of xn only gets counted the one time. And so this is the formula for the approximation of the area by trapezoids. And in the next example, we will look at how to use this trapezoid rule to compute areas.